Yes, I think we are live now.
Okay.
Awesome. Hey, hi everyone. A very warm welcome to each one of you. I hope you all are healthy, happy, and safe from whichever the part of the world you are joining from. For those unattended, DeFi is a global data science community, which we started last year with a vision to democratize data science education. And in our constant endeavor for the same, we keep on conducting boot camps, data challenges, and live sessions. Our today's session on BERT is one such initiative, and our heartfelt thanks and gratitude to Jayeeta for making it happen. I'm sure many of you would already know her, but for others, Jayeeta is a seasoned data science professional who is currently working at MediaMath as a data scientist too. She's an avid NLP researcher, loves to explore a lot of state-of-the-art models and build cool products out of it. Also, she's an active community speaker, delivered talks at various global conferences and events, and is very passionate about promoting initiatives to inspire women to take up STEM. Now, without further ado, I'd like to bring her on and let her take over the session. Thank you, and over to you, Jayeeta.
Thank you so much for the introduction, Yash. Hopefully, I am audible to everyone. You can hear me clearly? Okay. Hello, everyone. Welcome to the session. Thank you for joining today's session on DistilBERT and trying to learn more about natural language processing. I'm very excited to be here and speaking with all of you. I am currently based out of New York, as Yash mentioned, working with MediaMath. It's a global ad tech company where we are basically trying to understand user behavior, buying patterns, advertisement data, and then trying to model it out to see that what works best for and what kinds of campaigns, what kinds of advertisement work best for which kind of products. So it's a very exciting field, and yeah, I'm very excited to be here. So without further ado, let's just go forward. Here is a quick introduction about me. Hi, my name is Jayeeta. You can connect with me via Twitter, LinkedIn, or you can visit my website, and I'll be really glad to connect with you and then learn if you have any questions further after the session. So quick highlight of today's session's guidelines. I will try to make it 50 minutes of going through the slide and the code, and then 10 minutes for Q&A. As Yash mentioned, if you all need to get the code Colab notebook, I can also share it after my session. It's not going to be a problem. Just let me know. So what are we trying to go through today in today's session? So my goal is to kind of make the flow and the case of why NLP is important. What are some of the applications of NLP in the industry that I've seen in working in this space for almost close to 5 to 6 years now, and then where does BERT and all these kind of new state-of-the-art model comes into action, and what we can actually get out of that by using transfer learning and some of the other new concepts that we will go through today. So let's get started. So NLP is hard. Why I say this is because there is a lot of nuance in English language that makes NLP hard for the computer. So for us humans, when we see this image like electric metal fan standing, what is the first thought that comes to your mind? Human brain can quickly make connections and references and then say, oh, it's an electronic equipment. But then for the computer and the machine learning that's using this natural image, it takes a lot of training to make it understand that it could also be when somebody says I'm a huge metal fan, that concept can be tied to both an electronic equipment as well as if you are a huge metal music fan. So everything belongs, or everything is tied back to the context of the image, the text, the data that we are processing to be able to make useful information out of it. So some of the challenges of why it is a daunting challenge for the computer model is that because there's ambiguity, there's the case of synonymity, there's co-reference, and also a lot of syntactic rules that needs to be processed and trained correctly in an NLP model to make it actually give you accurate or close to accurate scores. We're not there yet. It's not accurate, 100% accurate yet. So going forward, I'm sure all of you have seen this diagram before because it kind of explains the space of AI, ML, and where NLP belongs in all of this. I really like this way of representation is because it also includes the most important area, which kind of gets like sidelined a little bit when we all talk about AI, ML, and DL, is linguistics, because in the NLP domain, understanding the English language and its nuances really can enhance and improve the scores that we are trying to get to, if we can include that in the way we are programming or cleaning the data sets or creating rules, etc. So think about it in a holistic learning domain, instead of like only trying to say, okay, which algorithm works best. Algorithms will only work best if we have that correct set of data, which is cleaned correctly, which is like understood correctly, and then processed in a way that is useful. And think about like how much text we see each day. There's like, science menus, like emails, like SMSs, there's web pages, Twitter, like there's data everywhere. So it's very crucial that that gets categorized correctly, segmented correctly, and then used in an NLP model. So just to give a little background of where NLP currently is, if you see the growth in the last 2 to 3 years, transfer learning has like the research that has taken place in this NLP sector has been like huge and exponentially increasing. Like recently, back in February, Google released their switch transformers, which kind of uses 1.6 trillion parameters. So if you see the growth, it started to get big when there was like, the TNLG by Microsoft came in, then OpenAI came in with 175 billion parameters, and then now it is at 1.6 trillion parameters. So with time, like the models keeps getting larger and larger and being trained on bigger data sets. So a quick highlight on where currently NLP has seen the major applications, and some of the areas that I have actually worked myself in the industry is in the machine learning, machine translation space. There's like, if you say want to translate English text to Bengali or whatever, whichever language, from audio to text, all these belongs to this domain or genre of machine translation. Example, like Google Translate itself is built on this technology. There's chatbots, very interesting, and quite a lot of applications. We will look at it in a little while as we progress with the presentation. So there's like intent classification. So the companies want to understand all the requests or complaints that coming via the chatbot, and want to segment it based on what is the intent of the complaint, and which branch it should go to, and who should take care of it, so that it's automatically auto assigned without manual review and QAs, which takes a lot of time and resources. There's also natural text generation, like abstractive summary and text completion is like a really like interesting space right now. Like a lot of research has been going on to make the prompts and the completion, the summaries, make it like as close to the meaning of the original text it is, and it can get very complicated with bigger, larger scripts of data. There's of course topic modeling that we all understand. There's like how better you can understand a piece of text, what all kinds of entity extractions you can do, and then like sentence chunking and some of the other applications in this space. And also there's like other text-based applications like sentiment analysis. There's also threat detection, a lot of social media, hate speech analysis in Twitter that is like a big area of application, and fraud detection in the insurance and finance space. So a lot of applications in the industry for these use cases. So so I'm not going to go into detail as we have like a lot of things to cover today, but I just wanted to highlight some of the very basic and the most important pre-processing steps that all the unstructured data that we collect for our use cases needs to be treated with. Otherwise, like I'm sure all of you have heard, like garbage in and garbage out, and that's the most I've seen happening in the text-based space, because it's so unique, and there's like no one particular way that you can treat your data to make it absolutely the best. It depends on your use case. So you have to understand what your business use case is, and then finally chart out that what works best with like testing it out, which method works the best. So the very basic ones, like, you have to, of course, treat spaces. There's also tokenization. Tokenization can be done in multiple ways. And there are various, the different packages that helps you bundle it. You can do it by engrams. You can like create different combinations of it if that serves a business case, and you can go that route. There's also spell check. I have seen this like as a very useful tool that you can refer to Peter Norvig's spell checker, which is like one of the very famous but very like baseline spell checkers that was released. If the spelling use cases, if the spellings are not corrected or there's like a huge difference in the ones, we will see how it affects later, because then we will talk about the concept of word to vec, or the vectorization embeddings of the words. And if these meanings are like not aligning to each other, then even though like you think that, oh, this concept belongs to that one particular domain, the machine will interpret as two different contexts because it got mapped to two different embeddings because the spellings were completely different. And we will see what that means in just a little later. There's also contraction mapping, which is very useful. Sometimes, like, there's in the free text, we say can't, won't, like didn't, and sometimes these needs to be cleaned based on how or what we are treating as the end product. There's also stemming, like basic, which just means that we have to go back to the, the base word of it. So if you see the example, it's like game, gaming, games, and everything goes back to that prelim word, which is game, so that we can process it correctly. And then there's also stop words. Now, stop words is a very tricky area. Like I have seen in multiple use cases that sometimes removing the stop words may or may not give you good increases in the accuracy. So it is different, definitely. And there could be other domain-based or your case-based stop words that needs to be taken care of. Like when I was working like on a legal document-based NLP, just removing the basic stop words was not useful. I had to also find out by talking to different other domain experts from the business side to understand that, okay, what other legal words needs to be taken out of, which doesn't serve the context of the meeting, but mostly are like fillers. And then there's also, case-based, like I mentioned, pre-processing step, like, if you want to do a POS tagging, which is like part of speech tagging, basically trying to understand the flow of the sentence, you could also do that using a lot of the good open source libraries that's out there. Now, let's talk about transfer learning and the significance of that in the NLP domain right now. Now, if you see these two architecture, what is one of the most important differentiation factor you see? So in the traditional machine learning segment, we have different tasks, and for that different tasks, we built different processes, and that creates a separate learning systems. What transfer learning helps us to do is that kind of bundle that learning that we did from those tasks. So say there were two separate tasks, the source tasks, we created a knowledge base, and using that knowledge base, we are trying to solve a much smaller target task, maybe that doesn't have that much enough data, and then we are leveraging that knowledge base to kind of create that new advanced learning system. Now, why do you think that we need it? Like, think of it from this perspective, that it took the team behind Google Brain like almost 3.5 days on 8 Tesla P100 GPUs to train all 340 million parameters of the large famous BERT-based model. So that kind of resources and time and complexity, maybe only the big organizations are able to achieve. But what if a company doesn't have that kind of resources to train such large models? And that is the concept behind using transfer learning. So basically, we are using the techniques, the learnings of all these big models that was already been researched, published by bigger tech companies that are open source, and then to achieve some of the state-of-the-art performance by simply adapting the pre-trained models for the use cases that we have on our own hand, and we will see how. So let's take an example. So say you have a data set one, and like I'm going back to the a very simple image classification example here to make the example more clear. So like say we have one data set, and X, which is we have like tags of what are the general images are. Like say it could be cat, car, tree, whatever, etc. And then we're using the data set, say like the ImageNet data set. So we create this entire, like say a neural network, not a very complicated one, but a very few layer one. And then the final y hat output would be what is the classified object termed as. It could be like a dog and whatever the identifications that it gets. Now say you have another data set, which is the data set 2, and it is a very pretty small data set. And the y hat, that the classified object that you need to find, is like if whether an image is an urban image or a rural image. So urban would be, big tall cities, cars, and like hard roads, etc. And then for rural ones, it will be nice green and a lot of open space, etc. That's a very generic example, but just to make my point clear here. So what we could do is that we could use the learning from the model that has learned the knowledge from the image recognition of the first data set. We understand the low level features like some of the edges, the curves, and then use that on the second data set, and then create this, update it in the final layer, which is the softmax layer, and then create this segmentation to not be it one-step segmentation, but segment it as urban or rural based on that final layer that we have updated in our process. So don't try to don't think that this is like the process is too complicated. I'm just trying to get across why transfer learning is needed. And even though if you don't understand each of the steps right now, we can talk about it in a little while later, but then this is the entire thought behind why transfer learning is so picking up in the current space. Some of the other examples, like say, even in the text recognition space, if you see the third example, we say we scrape data from all the general sources like news, blogs, etc., and then we want to understand the text recognition from only a particular sources of it. So we can utilize a model that was already trained on that behemoth of data, and then utilize that to kind of add our contextual data to it, and then learn from it instead of starting from scratch, starting from the beginning. And another example, like I just mentioned, ImageNet, millions of images tagged, but then you can use those to kind of utilize urban versus rural image segmentation. So when to use transfer learning, like I already went through a little bit of it, but when you have, say, you have a scarcity of labeled data, and creating a labeled data, trust me when I say this, like I've seen this happening so many times, and so many data science project that we have started came to a halt because there was not enough good labeled data, and it takes time and expert resources like involved to get them involved to make sure that the data that we're creating is actually good, there's no bias in it, or it has been cleaned and tagged correctly to what challenges we are trying to solve. So it is one of the big issue still in the machine learning market. And then there's also a thing that if you already have a pre-trained model with the huge data, so already you know that a network exists, like we created a very small generic, classifier, news-based classifier to basically understand what are the meta tags of it by just using Google's open source. And we didn't even have to utilize much of our internal data set because it was just a study use case. And we could just leverage the open source model that was generated. And another thing to keep in mind is that the task 1 and the tasks 2, so basically the data set 1 and 2 that you're using should have the same input properties. And that means that the transfer of knowledge would only be applicable if the features that the model learned from the first data set are directly able to get applied or used in the tasks 2 as outputs, right? Like if it cannot be like one is image, one is text, so there's like no concurrency between it. So what is BERT? Let's take a look at it. And before we go into the definition of BERT, I wanted to explain a very important concept to understand, which is the word embeddings. And word embeddings are nothing but feature vector representation of a word. And this is like an underlying, an underlying base of everything we do in NLP, because if the context and if the embeddings are wrong, none of the models will work or perform the way you want it to be. So this is just a very like a quick representation to show what the feature mapping means. So it means like similar words will be tagged or created or maybe positioned in that vector space in a closer knit platform than the others. Like say, so slowest would be like, connected to each other. There's Paris and France. These are some of the use cases. If you see the second one, like I tried to plot in a TSNE plot, if you see the areas here, like fish, eggs, and meat, they're kind of clustered together because they are like, food items that needs to be together, or the context or the meaning of the background words come from a similar type or a domain, similar to, like, say, fuel, energy, electricity, heat, oil. If you see the below portion here, it all is getting clustered together. And then there's also water, sea, ice, etc. Together. There's climate, wind, together. So it basically trying to show that all these words have meanings that are similar to each other. It's not the same, but it belongs to that same base platform. So this represents that vector space. Another clear example to showcase in a more mathematical format is to show that, okay, if you think of it as like, a vector space, a 3-dimension vector space, the words sky and engine and wings are the 3 vectors. And then if you see, the word helicopter, drone, and rocket is mapped with the vector sky and engine. And that's why the first one, 0, which is wings, because it belongs to those 3 words. Now, if you see the other ones like goose, eagle, and bee, they also belong in the sky because we know that they can fly, but they don't have an engine. They have wings. So that's why that got mapped to the other axis where sky and wings are the 2 vectors. And then, so this is how mathematically the models at the background store the data and understand the text, because we all know that computers cannot understand direct language, right? They transfer it into a discernible way in a numerical format to create meaning out of those general text that we throw at them. So that this is how they created the embeddings to create and cluster the similar words together. You can also try out, like, there's this projector.tensorflow.org, like it's just an UI. You can put, like, select the Word2Vec all model and then put any word of your choice, and you will see how it shows. In the screen, you can see that for the word politics, there's like economy, demographics, geography, nationalism, all these words are related words, and you can see the probability score that is being shared. So it's very useful information for the model that's working behind the scene to kind of understand what the context is, and context is everything in NLP. And that's why I love this image, which kind of shows that there's word vectors and there's context, and word vectors and context together make up the word embedding space, which all our NLP models learn from. Now, so there's been a lot of research and development in the NLP field, and each of these components is, of course, built on the the top of the previous ones by using their learnings, their outputs, etc. So one of the entry barriers that I've seen students, and even when I was trying or starting out in my career, to see that, okay, so do I have to learn everything in the previous steps, or do I have to know everything, like all the pi LSTMs, the RNNs and everything, and that's how, and only then I can be able to use or utilize the use cases of BERT? That's actually not true. And if you, I would highly recommend you go and look up Chris McCormick. He has like really good YouTube videos if you want to get into the space. And this is what he says, that this is what he calls as BERT mountain. He says that in order to be utilizing BERT, DistilBERT, or any of the state-of-the-art models, there are 2 other concepts that we need to understand. There is transformer and there is attention. What those 2 means, once you have familiarized yourself with those 2 concepts, it'll be very easy to kind of go forward and apply and understand why BERT is so important and how it is working, or what are the steps that it is taking in order to make the models much better than its predecessors, if that makes sense. So yeah, those are the 3 areas that we'll focus today. And then, yeah, just for fun fact, we all love transformers. So it may sound complicated and big, but then it's not that, and they are there to help us. So what are the general concept of transformers? Here it is. So there's like the feature vector is what we just spoke about, right? The word vector space, the word embedding space. And that's why I spent a little bit of time to go through that and what it actually means, to kind of show you how mathematically encoders like take, say, so this use case is for, a Google Translate is built upon the encoder decoder structure. So like say you have a particular sentence in English and you want to translate it into German or whatever. So the encoder will take the individual words from English. There would be a feature vector that would be created, and then that would get mapped out in the different language by the decoder. And this is like the highlight, and there is like backend models that's working for the encoder decoder, but this is the general idea of what it means. And then the structure could, like, not only for translation, for any kind of, say, like image captioning, for sentiment analysis, all kinds of these tasks, the generic concept behind is encoder decoder, that we are basically trying to encode a particular concept, be it image, text, words, and then decoding it into saying what the final output should be. Like, okay, if this is an angry tweet, if it is an happy tweet, etc., things like that. So bidirectional encoder representations from transformer is the full form of BERT. It's a mouthful, but let's look at what it does. So it has been trained, their trained model is based on the Wikipedia corpus and like the 800 million words book corpus. And what is the concept behind BERT? It's that it's the bidirectional means that BERT learns information from both the left and the right side of the token's context during training at the same time. And we will see what that means. So basically, the context parameter is crucial in BERT, and that's what we were talking about for word embeddings. And context meaning learning and, like, encapsulating the meaning of each adjacent word, both, like, say, leading and the trailing words of a particular word, to completely understand a sentence. And we will see an example right after. And then why is this a trendsetter? Because this is like the first deeply bidirectional, unsupervised, pre-trained on plain text. And it kind of outperformed on like a lot of general language understanding, like for language inferences, for sentiment analysis, for question answering, some of these tasks, but like outperformed some of the previous models. It also fixed another issue with the thing that we had in the previous models, was like how to handle out of vocabulary word, like say in the training context, you do not have any a particular word and that shows up in the test case, and then the model is going to not be able to identify that and will kind of fail out. So BERT kind of fixed that issue there as well. Now, like, let's look at a example here, like a context. Like, say we have a word called we went to the river bank, river being one of the word that we're trying to analyze here. And then I need to go to the bank to make a deposit. Now, bank is the common word in both the sentences, but it means completely different based on the context that it's coming from. So in the first one, it's like a river body, a water body, and in the second one, it's like financial institution. So how does a model differentiate between these two words? But by using the trailing and the leading words and understanding it at the same go, not in a separate states, but at the same state, by learning it left to right in the same way. So that is why that there are 3 embedding layers that BERT was built on to be able to do it the way that it solves the problem on. So there is this token layer, which is like individual tokens that we already spoke about, right? Like you can just segment each word in a particular sentence, and then that becomes your token. The position, so word to word relation is very important, because you want to understand where a particular word belongs in a sentence and what are the other words that it's just adjacent to that word. Maybe it could be a word that's just next to it, or maybe just before it. So that so the position tagging helps us with that. If you see the example in the position tagging, it kind of tags it as E0, E1, E2, and it kind of says that, okay, what is the order of the words that's present in a sentence. And then there's also segment. So segment helps in a multi-sentence complex structures. So we all know that in a text corpus, there can be multiple sentences, right? But we would also want to understand what is the relation between each sentence to the other. Like we cannot just jumble up sentences, that will make no sense. So that's why when you see the sentence embeddings, you see that it's EA tagged as A and then tagged as B, which means it's a different sentence, and that's how it is being positioned. And all these together creates that special mathematical model behind the curtain to kind of say that where it exactly belongs, which sentence it belongs to, what is the token, and then how are we learning from it. So that's how you're categorizing a particular word. So BERT was like pre-trained on 2 NLP tasks before. So one is the mask language modeling and the next sentence modeling. Let's see an example and it'll be clear to us. Like say the mask language modeling wants to understand, like if you have a huge amount of corpus and you're training on everything, there could be a chance that there are 2 perfectly similar sentences, and in that way BERT will be able, or the model will be able to identify the words in a way that's like, we could call it like it'll peek under the hood and cheat. So a way to handle that is like to mask a particular word and say, so the input would be the man went to the dash, which is a masked word, and he bought a dash of milk. So these are some of the masked word, but then in a lot of other cases, a lot of other sentences in the corpus, those words will not be masked. So then the test of the model, test the strength of bidirectionality of the model is to check if the labels are generated correctly. So the first label would be store and the second label would be gallon. And those are some of the ways that we will test if the BERT model is actually giving us correct outputs. And then the next next sentence model relationship is this is how it's done. So like say if a sentence says that a man went to the store, and then sentence B is like he bought a gallon of milk. So the label that is tagged in the actual training set is that it is actually a next sentence because it makes sense grammatically, it makes sense contextually, etc. But the second one, if you see the use case, the man went to the store and the penguins are fightless. Even though the two sentences separately make sense, they are correct grammatically, but then they cannot be like it cannot be said that they belong together. So it's not a next sentence, and that is how some of the the underlying way of how BERT works has been segmented to kind of answer these different questions so that together it can serve the purpose that we're trying to use in our use case. Now, I just wanted to touch upon a small, I would really encourage you all to go and read some of the blogs that Jay Almar has up. They're like really informative. It's very visual. It lets you understand the concepts very clearly. And I really like the way that he has put it here is to show that what does attention mean? Now, in a complicated sentence, we use prepositions, nouns, etc. How is the model going to learn that which word belongs to a particular word? Say in this example, it says that the animal didn't cross the street because it was too tired. So how do we know that what it is talking about? It can also, there are multiple subjects, like there's animal, there is street, there is tired. So how do we know that what it belongs to? Like humans, we understand, oh, we are just referring to the animal because it's just, but then the model itself may or may not be able to understand. And that's where encoding comes into play. It says that the part of the attention mechanism was like the focus on the animal, and this is how the representation of the it is encoded in the model. So that's just like a very generic highlight, but please, if you are interested to learn more about attention, there's a paper called Attention is All You Need. You can also look into that, but also look at some of the graphical explanations that Jay Almar has published. Now, this is where we are in the biggest challenge, and I have seen this in like while democratizing or productionizing some of the models, is that how do we put these huge models into production? Like they give you, say, like an amazing score and you are very happy with the results, but then when you have to put it into production and it is running in real time, it is very, very crucial that it happens very fast and quick, right? And sometimes these models does take time. There is latency issues. So for some of the use cases where latency is like has to be like negligible, like say for in the AdTech world, like when we serve an ad or we pass a bid in real time, it has to be like real time. Like the example is like when you open a website, say, and you see the ads popping up in the side of the pages, it happens real time by the time the website actually loads. So there's like there cannot be any latency that comes in. Otherwise, it's going to be like a huge problem for the business. And also we need like really costly GPUs or servers to serve at scale. So how do we handle that? We handle that by this potential solution, which is called like as the knowledge distillation. So what is knowledge distillation? Think of it like as a technique to kind of compress that entire large model that we were talking about, like say the BERT-based model, and call that as a teacher. So the teacher has taught everything, they understand everything, it's a huge, accurate model. And now we want to transfer that into a very small model called the student. Now, what it does is basically what the compression technique does is basically reproduce the behavior of the large model into that small model And it doesn't have to even go through the entire training process. We're basically extracting the knowledge and the distribution of that knowledge into the smaller model so that it can understand where it's coming from. So how it is done? So in the teacher student training section, like say a student network is trained to kind of mimic the full output distribution of the teacher network. We'll see an example in the next slide. But what it means that is like, say you have a use case and you use BERT model to kind of understand or predict something, and you have an output distribution for that, right? The student model is kind of trained to mimic that output distribution so that we understand what that distribution should look like and what is our goal purpose so that we can meet that. Now, a quick example here is that the like say you have you have a sentence that I think this is the beginning of a beautiful dash. Can you see the masked word, right? So when we are predicting, this is the guesses that a BERT model took for completing this code, and then it ranked from 0 to 19 multiple words and gave a probabilistic score that what it thinks should be a good word for that particular masked word in the sentence. Now, so the idea is, like in the supervised learning, a classification model is generally trained to predict like a final goal class by maximizing its probability, right? Like using softmax or logits using the log likelihood signal. So in many cases, a good performance models will predict the output distribution with correct class and have a high probability. So how can we use this predicted output section and train the student network to kind of mimic that is the goal that DistilBERT has achieved. Now, let's say for one example, a desk chair might be mistaken with an armchair, but should usually not be mistaken with, like, say, a word mushroom. So we are almost there. It's not perfect, but we are understanding the flow of the output and taking into consideration of all the correct answers that could be. And because there is like this uncertainty, sometimes this is referred to like as a dark knowledge from the teacher that it takes. So DistilBERT kind of trains the student to generalize the same way as the teacher by kind of matching the output distribution of the teacher model, which in our case is word-based. I know this is like a lot of information, and I'm explaining it in a very high level way. If you have any questions, please let me know and we can go through this later. But to go forward, it's like, so using the teacher the signal, a smaller language model, which is the DistilBERT in our case, was built from the supervision of BERT, because we follow the output distribution of BERT. And DistilBERT's 66 million parameters make it like almost 40% smaller and 60% faster on than BERT base, and retains like almost 95% of BERT's performance. Great. Now, what is the application that we want to apply here? So one of the application we did apply this in one of our work projects was like to build the Q&A model, which is like a question answering model. So this is like a very general overview of what a question answering model looks like. So there's like question processing, we do question analysis, the classification, and there's also a lot of time that we need to reformulate the question, because we cannot just pass the way that it came from the user, right? Like it needs to be processed, cleaned, like via all the steps that we discussed before. And then that goes into the document processing step, which basically shows that, okay, there's like information retrieval. We also have a backend knowledge database. We kind of go match to see where that question belongs to. And that is where, when I was saying that intent classification came into action, that we want to understand that which path we want to send the question to get the correct answer retrieved from. So there's like paragraph filtering, where it is, where it should set from, which domain it should come from. And then there's also answer processing. So basically the answer identification, the extraction of the answer from the document knowledge database, and then making sure that the answer is correct. So there's like also a validation step that we need to do in order to make sure that the user is getting the answer that they expected to get. This is just like a highlight of another of the same use case to kind of show that, okay, if you say, how do I reset my password? You say, okay, let me review my password, let me review your account, and then the steps you see 1, 2, 3 that the example shows, it kind of shows that where the user can go to kind of identify steps to update their password. This is the actual final step we'll see in the code in a little while of how the question is going back and retrieving the answer from. So if you see here, this is the context, like context of a news article or whatever, and in the text in the question we asked that, okay, when did Beyonce start becoming popular, and we could find the answer in the context, exact answer. If you see, it's highlighted in green, in the late 1990s. So that was retrieved from the context, is one of the steps in this entire question answering building system. So we went through a lot of theory here. Now let's quickly take a look at a very simple demo, and we will see that how that works. Okay, I hope all of you can see the Colab notebook. I could also share this after our session, so you can take a look, and please let me know if you have any questions, or we can, go in details. So one of the best thing about open source that I like is that there's like so many good models that has already been trained, and transformers model that was released. So if you you can go forward and learn more about transformers and how to install them. But this is the way that you kind of install the one and the torch to kind of go through it. So let's look at a very simple use case. Like, say, from the transformers, we are importing DistilBERT tokenization, and for the DistilBERT question answering, the idea is that if you have a context here, right? Like, say, if you have a context that, okay, case numbers, so COVID case numbers in the United States have like fallen to the lowest, etc. This is a text from, like, say, a news article or whatever. What we are trying to do here is that already using the tokenizer that was created by the DistilBERT tokenizer from the pre-trained model called the DistilBERT BERT uncased. This is the the student model that we just spoke about from BERT base. And then we are using that model again. So this was the tokenizer, calling the tokenizer from the pre-trained model and calling the actual trained model from the DistilBERT based uncased model. And this is the context that we are providing. Now, this model that was created actually was trained on multiple other huge amounts of data set that we just saw, and we don't know what it was built on, but this is the new context that we are serving them. So we are saying that, okay, let's build on top of it just to see that how well it can, understand the English text. But if you consider using it like say in a very generic NLP use case where you had no other information and you had only this much of text data, it would be like impossible to train a model from scratch up, because it's not enough data, it's not enough context, there is not enough word embedding for the model to be able to recognize those. So then we will fail overall. But then in this way, you already have a baseline knowledge where you're basically extracting the information from and using this context in the last layer to understand or get your answers of how you're trying to answer it, basically. So like, say the question is, what was President Joe Biden's announcement? What we do is, like, you call the encoder and you use this tokenizer. It gets tokenized in a correct way. It starts scoring by using the scores that is already there in the trained model. And then when finally it kind of converts the tokens, you see that this is the final tokens that it identified in the entire sentence. So it says that, okay, its administration is like donating 500 million. Here it says, where is it? Sorry. Yeah, it's here. Like, his administration is donating 500 million doses of Pfizer vaccine. And that is what the announcement was all about. And then when you just aggregate the entire tokens to make it as a sentence, which becomes the answer here. And it also says, okay, how many deaths have been reported in the virus in US? And then you see that it says that cases of this many deaths have been reported. And we see that the answer token that was identified, sorry, was exactly the same as the characters we see over here. And then the final question was like, okay, how many total cases have been reported? And we see that 33.4 million was extracted from the entire context that we served in the model's final length generation. So this is like basically a very simple way to kind of give you an example that how a pre-trained model could be used by adding simple context. But in an industry use case, it is not as simple as this, because when we were dealing with our chatbot data, it kind of had a lot of other kinds of nuances to be taken care of. It was not only English language based, but there was like, technical terms, specific, company based product names that was nowhere present in the training data set, right? So then we had to create like a really good amount of clean data set to kind of make sure that all these extra information was captured. And once that was captured, then the model will be able to leverage the pre-trained model, which is on a very generic scale and trained on a very generic data set and not your business use case focused data set. So if you are thinking of implementing this in your work and in the space that you're working on, you should always make sure that the context that you're providing should be very, very focused on the business use case. And only then the models will be able to leverage the pre-trained models. Otherwise, you'll still see very fluctuating results. So a lot of that. So what's going on with NLP now currently, right? So there's like a huge amount of work that's going on from all the big tech companies. And I came across the beta release of the Google's Mina, and it supposedly it can chat about anything and like anything. So they can execute a multi-turn joke and in the open domain setting. So it says that, okay, if the human says like, I like cute cows, and then they come, and if you read through the examples, you'll see it somewhere that it talks about like, horses going to Harvard. And then Google mentioned that in their training data set, they couldn't find any such information that was given to them. So basically they're coming up with the joke by themselves by creating patterns from the data that was already used to train. So this is like a huge step forward, and there's like a long way to go, but then there's a work in progress, I would say. And this is a big number. This is the number of parameters, 1.6 trillion parameters that Google switch transformers have released. And why I mentioned this again here is because of this. And if you see the estimated cost of training a model, like this data was pulled from MIT's 2019, I guess, paper. So it still hasn't included the cost associated with GPT-2, GPT-3, and some of the other new models. But even then, the staggering cloud compute cost and the energy consumption is like huge for this transformer and big data models. So the side note is like training a single AI model can emit like almost as much carbon as 5 cars in their lifetime. So why the transfer learning concept is getting so much or picking up in the space, in the NLP domain space, is that we need to understand how to effectively utilize resources and not just keep training models just for the sake of it. So if you can utilize something that's already there and build on top of it slowly without being like, saying that, no, I have to do everything from scratch and I'll just build, doesn't matter, it takes millions of dollars for the industries and the companies. And this actually goes back to the industries more than the users like us. Like we do not even have the capacity or resources to run all these models and create all these models from scratch. So that is why the being vocal about the applications or consequences of this is also very important, to be aware that we're not misusing resources that we have currently and only take advantage of whatever we have already available. So yeah, this is just like a few insider tips. So yeah, make sure that the data is clean, because bad data cleaning makes NLP like super hard, because there's like no way you'll be able to understand if the computer, there's no way for the computer to understand if something doesn't make sense, and it's you that needs to be able to give them the proper data to understand. And sometimes it feels like most of the companies I've seen, they talk about, okay, we have to apply neural networks and recurrent neural networks and all the big hi-fi advanced solutions. But sometimes it happens that we don't even need advanced NNs for some of the best solutions that I've seen. And even a logistic regression model with a very great like hyper-tuned model worked the best and outperformed almost all other applications that we were testing. So sometimes it depends on your business use case and the data that you have at hand, and that would dictate what algorithm and what process that needs to be applied, and not the other way. That we shouldn't say that, okay, I want to apply a neural network, this is the data I have, let's go for it. That will not give you the correct results or the desired results. Here are some of the additional resources if you're interested to learn more about the BERT paper, the attention is all you need paper, the blog that I was talking about from JLMR, all it is listed here, and you can take a look at it and learn more about it on that. So yeah, thank you to the DeFi team. I know I went through a lot of content very quickly, but I wanted to have a little bit of time to see if you guys have any questions or any other anything else that you want to talk about. So thank you for that. You all can connect me via my LinkedIn or like this like a website. You can go and we'll have the LinkedIn and website connections. I'll be happy to keep in touch and answer any other questions that you may have. I think that should be all from my side. Yep.
Thank you so much, Jayeeta, for such an insightful session. I'm sure the community thoroughly enjoyed learning.
Sure,
there are a couple of questions from the learner.
Sorry, yes, your voice
asked,
is. Hi, sorry, yes, your voice is breaking up a bit. If you could repeat that once again. Like I was not
sure. Is it better now?
Yeah, this is better.
Awesome. So he had a doubt around the code that you showed. So he asked, in the code, the tokenizer is student and model is teacher. Is it? And can we choose teacher student of our choice, or what would be the criteria of the choosing?
Criteria of the student. So here in this case, when I say teacher student, the teacher is basic. When I was talking about the teacher student example, is that what I meant, that DistilBERT was created as a student from the BERT base model, which was the teacher and had like humongous amount of parameters. So when the DistilBERT pre-trained model was generated, it was created in that way. So when we are pulling the model or the tokenizers, we're actually pulling it from the DistilBERT and not the BERT base directly. So in this case, if you're saying that you would want to choose the student or change in a way that the combination of the student teacher, I don't think that is the case, because like say if you are using a particular model, DistilBERT, which is a dialed down version of BERT, then in this case that is a student and that is the model that you're pulling from, if you know what I mean. Like I don't think there is a way to kind of say that, okay, I don't want to use DistilBERT as a student, but I want to use something else. But that something else needs to be already pre-trained and available for you to pull and create that comparison, is what I mean.
Got it. I hope the doubt of Subramanian is clear now. Another question which we had, and a very interesting one. So for the learners or for the beginners, like how should they decide, whether to choose BERT or DistilBERT, or how do they generally go about it in the industry?
Yeah, so this is actually a problem that exists because we have like so many models that keeps coming out every day, and then there's this also the asks from the industry leaders that, okay, can we apply the state-of-the-art model in there? So now it kind of falls on the data scientist or the person itself who's learning to kind of advocate for the models themselves, saying that, okay, for this kind of use cases, these models actually make sense, and you'll only be able to do it when you kind of have learned it scratch up. So that's why when I was saying that in order to learn BERT, we need to understand the transformer and the attention architecture first. And once you have done that, you'll be very able to very easily be able to say that, okay, for this kind of classification tasks, I think we can use BERT, but for the other ones, we can use some kind of other models. And sometimes, like I said, that I've seen like it happening so many times that we started building out, like a very recent example that happened, that we created multiple models. Like there was a tree-based model, there was logistic regression, there was neural networks, and then the logistic regression model with hyperparameters tuned actually outperformed the neural networks, and that have replications, right? Like when the business comes back and says that, oh, you're not using the state-of-the-art model, you should be able to explain to them why you are not using them, like show the results, show what the results mean, and explain that for this kind of data, maybe the data was not big enough for neural network to kind of identify correct resources. Maybe it was too like, the two imbalanced data. So sometimes it happens that if it's a hugely imbalanced data, it's not able to learn the correct parameters by using the linear architecture. So there should be, I guess the best way to put it in a way that is that you need to be first able to understand how to differentiate each algorithms, and you'll only be able to do it is that you learn it step by step and like not try to test out on everything. Like if you have tested out in one, great, go and learn the next one and then try and see if that is comparable score or not, because like clarifying or discussing it back with the businesses I have seen is like very, very useful, and they kind of depend on the data scientists to kind of make this use case and say that, okay, what works best, instead of like throwing it on whichever state of the art model there is.
Got it. Totally makes sense. Yeah. One more question which we have. So a learner like isn't a bit clear about the concept of transformers, so maybe like we have a couple of minutes left only. So if you can it's about the concept of transformers, which you earlier talked about, so that he's clear about it a bit.
I'm really sorry, but your voice like really broke up and I couldn't hear the entire question. So you're saying that we want to learn about transformers more?
Yeah, is it better now? Am I audible to you?
Yeah.
Yeah. So if you can, quickly just cover about the transformer, basically just give a quick overview, right, in a couple of minutes, so that the learner is clear about it.
Okay, yeah, sure. So the concept of transformer is to basically solve like, a lot of this sequence to sequence tasks. Like say you have an entire sentence and you want to translate into a different language. How do you do that? The step is to kind of break it down. And that's where that encoder decoder process came when we showed that through, right? So you are encoding that entire sequence, and then you are creating that feature vector representation inside that kind of gets structured and then decoded in the final step. So what transformer basically does is that it's just like an architecture that solves this sequence to sequence task and handles some of these long range dependencies. And when I say long range, again, that concept of self like attention comes in. It's because like say you have prepositions, multiple other words that map back to the same subject. Like in our example, it was the animal. So how do you make sure that it gets tagged to the same back subject without losing the representation of the word itself? So that is the overall view of what transformer is trying to do, but it's doing it with like a combination of help from the attention, the encoder decoder in the input sequence, and then attention in the output sequence. All of these together kind of builds the concept of transformer, is that you're transforming one particular object. Maybe it is an image, or like if you want to do an image to text transfer, so then input image of the transformer will be that particular image and the output will be the text. So you're utilizing all these steps to kind of transfer that. And then same for translation, your text transforming text from one particular language to another particular language. So it basically kind of creates that hidden layer of understanding of how to map back, create that input sequence, map it to all the words in the using attention in all the input sequence, and then map it back to the output sequence to make sure that it has not lost the meaning in translation. So that's the overall hood that transformer refers to. I think that I think in such a short time, that's like the simple knowledge that I could give, but I'm happy to discuss. If you have more questions, please reach out to me and I could share like some of the other resources that you can review to learn transformer in a better way.
Got it. Yeah, cool. I think like it's clear to him now. He also committed thanks for that. Cool, awesome. I think like that's pretty much for the question. Once again, Jayeeta, thank you so much for such an insightful session. Like we can clearly see like the audience loved it. And thanks everyone for joining in. We hope you enjoyed the session, and wish you a very good day ahead. Bye bye.
Bye. Thank you. Thank you for having me. Thank you, everyone. Bye.